All right, let's dive right in. Welcome to today's explainer, where we're going to dismantle one of the biggest and honestly most widely accepted everyday lies we tell ourselves. We're talking about a fundamental cosmic misunderstanding that completely blurs the lines between what we're actually made of and how the universe pulls on us. It's a physics mix-up that happens in our bathrooms, in gyms, and in doctors' offices literally every single day.
I want you to picture a super familiar scenario. You wake up, you step onto your digital bathroom scale, and you look down. Let's say the screen flashes and gives you the number 60. In your head, or maybe even out loud, you probably think, okay, my weight is 60 kilograms. It's totally standard everyday language. But is it actually scientifically accurate? Is that number genuinely measuring your weight?
Well, the short answer is a resounding no. Scientifically speaking, 60 kilograms is your mass, not your weight. In our daily lives, we constantly and incorrectly use the term weight when we're measuring ourselves in kilograms. We've literally swapped two totally different scientific concepts. So to understand why this everyday phrasing is technically a lie and how we actually calculate the truth, we need to separate these two terms and look at the actual data.
Section 1. Mass, the unchanging constant. So what exactly is mass? It's simply the total amount of matter present inside an object. Think of it as a raw tally of all the atoms and molecules that make up, well, you. And because it's just a raw count of matter, your mass is an absolute constant everywhere in the universe. Its value doesn't change. I mean, if you were to teleport to another planet right this second, your mass would be exactly the same, because the actual number of atoms inside of you hasn't changed one bit.
And this actually brings us to a brilliant illustration of Newton's first law of motion. See, mass isn't just an atomic head count, it acts as a direct quantitative measure of an object's inertia. And inertia is just an object's inherent resistance to a change in its state of motion. So higher mass directly means higher inertia. The more matter you have, the harder it is to get you moving if you're standing still, and the harder it is to stop you once you're already going. It is a fundamental, built-in property of the object itself.
Moving on to Section 2. Weight, the gravitational pull.
Now let's see what happens when we introduce the external variable of gravity into the mix. This definition completely changes the game. Weight is not what you're made of. Instead, the weight of an object is defined as the net gravitational force with which the Earth, or whatever planetary body you happen to be standing on, attracts that object toward its center. It's an interaction. So, unlike mass, weight is a variable. It changes from place to place depending entirely on the local pull of gravity, which physicists refer to simply as g.
The absolutely crucial takeaway here is that weight is a force, and mathematically, it's derived directly from Newton's second law of motion. You probably remember that one. Force equals mass times acceleration, or F equals ma. Well, when we calculate weight, the force is the weight itself, represented by W. The mass is our m, and the acceleration acting on that mass is gravity, or g. And that gives us the vital equation, W equals mg.
Let's actually apply that to our bathroom scale example from earlier. If your mass is 60 kilograms, we have to multiply that by Earth's average acceleration due to gravity, which is about 9.8 meters per second squared. So 60 times 9.8 equals 588. But it's not 588 kilograms. Because weight is a force, your actual scientific weight is 588 newtons. The newton is the official SI unit for weight. Honestly, the next time someone asks you how much you weigh, if you want to be perfectly scientifically accurate, you should just look them in the eye and say, 588 newtons.
All right, Section 3, the core differences. When we put these two concepts head-to-head like this, the distinction becomes crystal clear. Look at the basic nature. Mass is the total quantity of matter contained within a body, whereas weight is the gravitational force acting upon that body. Check out the SI units. Mass is measured in kilograms, while weight is measured in newtons. And finally, variability. This is the big one. Mass is constant everywhere. It is a permanent property. Weight is variable. It relies completely on the local gravity of your environment.
If we push the math just a little bit further, we hit another core difference. Mass is what's known as a scalar quantity. That means it possesses magnitude only. It's literally just an amount. It has no specific direction. Weight, on the other hand, is a vector quantity. It possesses both magnitude and a very specific direction. Because weight is a gravitational force, it is always directed vertically downwards, pulling straight toward the center of the Earth. Which leaves us to Section 4, the lunar thought experiment.
Let's take these abstract concepts and apply them to a really cool off-world scenario. Imagine an astronaut traveling from the Earth to the Moon.
As we've learned, their mass remains totally identical during the flight, right? Because the actual number of atoms in their body hasn't changed. However, because the moon is much smaller, its surface gravity is only about 1/6 of Earth's. Therefore, going back to W equals mg, that 1/6 gravitational pull slashes their weight drastically. Their weight on the moon drops to exactly 1/6 of their weight on Earth, even though their physical mass is exactly the same. It is a perfect demonstration of just how variable weight really is.
Which brings us to one final kind of mind-bending scenario. What if, instead of flying to the moon, you managed to dig your way all the way down to the exact center of the Earth? Well, your mass remains constant, right? It can never be zero. But down at the exact core, the gravitational pull from all directions essentially cancels out, meaning g becomes zero. If weight equals mass times zero, what does that mean for you? If your weight literally disappears entirely, how would your body even react to existing in a state of absolute zero weight? I'll let you ponder that zero-gravity puzzle until next time.